So you can see the team here, and this work is a collaboration between the University of Notre Dame and the University of Central Florida survey class. And you can also see that Clive Neal and I work at what may be the longest department name in all of academia. If I said it right now, my 8 minutes would be up. So I'll give you a brief outline here. I've got a background in methods, and I'm going to walk you through several correlations that I've developed between cone penetrometer testing data, which I'll use CPT from this point forward, and bulk density of lunar regolith simulants. I'll give you a sneak peek regarding work that we've done regarding replicating Highland's near-surface regolith stratigraphy at the Apollo 16 landing site in the lab. And then I'll also give a shameless plug for more work from our team from Longfox et al. Immediately following my talk. So don't go anywhere. So I'll start off by telling a story, and I love this story because it really nicely emphasizes one of the points that I'm trying to make regarding lunar regolith simulant using it in the lab, and that is shortly after the Apollo 11 mission returned from the moon, NASA technicians had Buzz Aldrin walk on a simulated lunar surface, which was quartz sand about 15 centimeters deep. And there's a picture of Alan Bean on that same test track. And after that, the technicians asked Buzz Aldrin how that compared to walking on the actual lunar surface. And Aldrin replied that the sand was too yielding. While walking on the surface of the moon, he noticed that the regolith was soft at the surface, but he could tell that there was a firmer stratum underneath. So basically the lesson here is that when working with simulants in the lab, to pack them in specific bulk densities to try to recreate the actual near-surface lunar stratigraphy while performing Earth-based testing. And so the objective here is to understand how regolith will withstand construction and other surface activities. It'll be critical to replicate not only the geotechnical properties of the lunar regolith, but also the density profile of the near-surface regolith as well. And so here we use Exolith Lab lunar simulants to develop correlations between CPT data, cone penetrometer. I use CPT here throughout the talk, and bulk density, correlations that will be essential for replicating near-surface regolith conditions in the laboratory. And so Apollo 16 geotechnical data included drill stem, drive tube, and also cone penetrometer testing. And you can see here a video of Charlie Duke using the self-recording penetrometer on the surface of the moon. And you can see he took a little spill there. Now I've put on a little weight lately, and the bigger they are, the harder they fall. So hopefully it doesn't happen to me as well. But the geotechnical data from Apollo 16 showed that although along the landing region of the moon for Apollo 16, the stratigraphy, the near-surface stratigraphy was locally variable. But there's a general similarity between stations 4 and 10 in that a firm layer is encountered about 5 to 10 centimeters below the surface. Then resistance increases significantly to where there's a firmer, denser layer at about 15 to 20 centimeters below the surface. Now, this interpretation is reinforced by the Apollo 16 LM. And although the descent engine nozzle here rests only a few centimeters above the surface, you can see that essentially no blast crater was produced. So apparently this less dense layer was blown away, leaving the denser, firmer layer exposed. And so let me move on to methods. And so we used a RIMIC CP40 cone penetrometer. You can see it in the cartoon here to measure penetration resistance values versus depth for lunar simulants packed at various densities in our clear plexiglass bins. And the clear plexiglass was a nice feature so we could see our simulant columns in cross section, and also to perform measurements and take photos and such. On the right, you can see a plan view looking down into our simulant bins, and you can see my Purina pattern of 5 insertions per packing. And you can see the data here in the colored curves. Anyways, so we use these raw data here, and this is for LHS1 packed at 1.71 grams per centimeter cubed, determined the G-slope parameter, which is simply the slope of stress over depth for these curves. Now, we've been working with Exolith Lab to perform correlations for multiple variations of simulants. And at the right, you can see how these G-slope correlations are performed with 1-layer simulant packings with our cone penetrometer. Now, this correlation here in the plot is for LHS1 dried simulant, and this consists of 45 CPT measurements. So it's 5 insertions each at 9 different density packings. And you can see that we've got a strong exponential correlation here. Note the log y-axis here. And so I've got more correlations here for LHS1. And here on the left, I've got LHS1 undried or ambient simulant, which in our lab, we measured about 800 ppm water content. And on the right, we've got a correlation for LHS1B bulk simplified simulant, which is a simplified lower cost simulant for larger scale engineering tests. And it's essentially LHS1 high fidelity minus the trace minerals. And you can see again, we've got correlations. Note the bulk density range and the G-slope parameter range here, which the data fall within the range of measured G for Apollo 16 stations 4 and 10, which is the gray dashed lines. And then so here are 2 correlations for Lunar Mari simulant, LMS1 dried and undried. And here we were using a 1.29 centimeter squared cone in the laboratory. Well, all self-recording penetrometer data from Apollo 15 was used with a larger cone designed for softer soil, so we can't really compare too well this range measured at Apollo 15 with ours. And so you can see that all these correlations show very strong exponential relationships. And also, we're able to compare, for example, undried versus dried simulant, high fidelity versus simplified simulant, comparisons that will really help us kind of select the appropriate regolith analog to replicate the lunar surface conditions in the laboratory once we start going to the moon with robots and humans. And so quickly, I'm running short on time, but I've only found 2 other similar G-slope correlations in the literature. I show on the left here, Oravec et al. For GRC1 simulant, and on the right, I show Yusin and Namik for a crushed basalt simulant. These are the only 2 that I know of. So if anyone in the audience knows of any others, pull me aside and please let me know. And then let's see. So here's my sneak peek about tests that we're submitting for publication here. They're 2-layer tests to replicate the Apollo 16 Highland stratigraphy based on data from the mission. On the right, you can see a picture of our 2-layer regolith column. And the blue curve here is our laboratory data. The black curve is that laboratory data adjusted for lunar conditions with a reduction factor of 0.29. And you can see that closely follows the data taken in situ at Apollo 16, especially for station 10. And I'm short on time, so basically the bullets on the left there are what I just said, except for future work includes G-slope correlations for Exolith Martian simulants. And I've put a couple applications there that you can read while we're talking. And so thanks for your attention, and I'm happy to take any questions.